Hello, everyone. This is part two of tension member, designing member element in trusses. So in this lecture here, we're going to go over some general information that we need to understand before solving any problems. To start with, all the trusses members are rigid except their connections. Some of these connections are non-rigid, and because of that, and not only because of that, but also it just because the intention of this lecture to focus on the connections and understand the mode of failures, whether it's rupture or tension, we are focusing on this part. So let's look at a simple truss here. I apologize if the drawing is imperfect. Let's say we have a truss looks like this with vertical elements, as you can see. Let's assume that our loads are acting downward on the truss elements. Those chords here, the bottom chord, are in tension all the time due to the effect of the load downward. Those elements here, the vertical elements, sometimes in tension, sometimes in compression due to the end alterations. But what we're looking at mostly are those connections here. Those connections are due to a lot of mood failures. The two of which we are looking at is the rupture and tensions. Those are non-rigid and very critical. So we're going to focus mostly on them. In this slide here, I'm going to go over the procedure of the design. I was thinking to leave this for you to read and understand, but then I thought about it, and because we've been doing this since the beginning of the semester, going over the procedure and understanding each step of the procedure, I find it very effective with you guys. So I'm going to do this here too. So starting from step one, it says determine the critical combination of factors load or factor loads. What do we mean by this? So the load combination, and you don't have this in the textbook, so I would recommend writing those down. You don't have to memorize them though, but you'll need them handy because you will need them a lot. We have 7 cases here, load combinations. And it depends on the system. You could use one case or you could use multiple. It depends on the problem statements and the giving in the problem statements. So if your problem statement indicates only dead load, then this is the only case you should use, case number 1, 1.4 times the dead load. But if your problem statement indicates dead load, life load, and either roof life load or snow, then you should use this case. The second case indicates the dead load, roof life load or snow, and life load times F, which stands for the occupancy factors, or the wind, then you should use case number 3. Case number 4 is when you have dead load, wind, life load times the occupancy factor, and or either one of the roof life load or snow. Now, case number 5, we're not gonna cover in the scope of this lecture or the scope of the class, neither case 7. So you don't have to worry about these cases here. Case number 6 though, if you have dead load and snow, then this is your case. Again, you could use either an individual case or multiple cases, depends on the problem and the givings in the problems. So going back to the step number 1, that was the step number 1. Step number 2 is for each critical load combination, determine the gross area required by equation 9.1 and select a section. Now, as far as equation number one, if you remember, it's PU equals 0.9 Fy times the gross area. So they want you to determine the gross area according to this equation, which is the yielding in the gross section area due to tension, right? Remember the two mode failures? This is the first one. And then make a provision for holes or welds based on the connection requirement. So you need to know if your connection is welds or bolts, and then determine the effective net area. The effective net area is the effective net area found from the net area. Now, why do we have to find this? Because at step number 4, it tells you to compute the loading capacity of the effective net area of the elected section by equation 9.2. Now, equation 9.2 is PU equals 0.75 times FU this time times the effective area. So effective area is here. FU is the maximum load capacity times 0.75. This capacity should be more than the design load step. This capacity here should be more than this. If not, revise the selection. Then your selection is inadequate and you have to change it. Then step number 5 tells you to check the block shear strength with equation number 5. Now, equation 9.5 is when you have the effective area equals to the net area, which should be less or equal 85% of the gross area. Right? So then you need to check the block shear according to this equation and see if it's not adequate. Then you have to revise the connections. And as far as the limitation of the slenderness, we said, if you remember from previous lectures, we said the 300 is the maximum we should stick to. But in the code 2010, they said it's not mandatory. You can't go above this as long as you can check and verify. But my personal opinion is to stick with the 300 just to make sure that you're adequate and you're not over designing. So for that, I would stop here and continue on example 9.5 in the next lecture.